Okay, so today I'm going to tell you about quantum computing tools for quantum chemistry. So I'm going to first start by giving a short introduction about quantum chemistry. Then I'm going to give a just quick overview about quantum algorithms, and then I'll tell you about some of the tools that we have been developing at QunaSys for chemistry. So in working on quantum simulations, there's different types of problems one can study, such as quantum chemistry, quantum molecular spectroscopy, or chemical quantum dynamics, correlated electronic structure, which is more condensed matter physics in materials, and also dynamical quantum effects in materials. And we focus mainly on quantum chemistry. So in quantum chemistry, like the wave function contains all the information about the electrons of a given molecule. And this information can be used to compute all the different properties, such as the energy, the structure of the molecule, the reactivity. However, this can be quite challenging when you're dealing with big, complex molecules because of the complexity of the electronic structure. If you take a look at the molecule on the right, you can see that this has a lot of electrons in it, and it can be very hard to compute exactly what goes inside of these molecules. So for those of you that have background in computer science or in mathematics, you might know about complexity theory and hard problems. So here on the left, you can see like different classes of complexity. And most of you have heard probably about the P versus NP problems, where P is the polynomial time problems, or NP is the non-polynomial times problems. However, for quantum systems, what we are interested in is more these, if I can get my pointer there, these other type of problems, which is called BQP. So these are the bounded error quantum polynomial. And what is good is that this is typically the class of problems in which quantum dynamics fall into. And it is known that they can be efficiently solved using quantum computers. However, there's another class which is not shown in this image on the left, which is the quantum Merlin-Arthur problems. And this is the class of problems to which the finding the ground state falls under. And unfortunately, these are problems that are not known to be efficiently solved even by quantum computers. And one can think about the relationship between BQP and QMA as similar as the one between P and NP. So this is from a complexity perspective. So if we look at it directly from orbitals and chemistry, if I can move to my next slide, there we go. So there's different types of problems, which like one are single reference, and the other ones are multi-reference problems. So in the single reference case, these are problems that you can determine by just using a single slated determinant. Whereas the multi-reference, as you can see on the right, for this one, you need a linear combination of multiple and often very large number of slated determinants. And you have here in TL the active space that you need to take into account for determining like finding the correct wave function of your problem. And as you can see, this makes it a much more difficult problem to solve than if you had only a single reference situation. And examples of systems that are multi-reference is, for example, the chemistry of enzymes. So you need to find the active sites involved in multiple coupled transition metals. And another one is the transition metal nanocatalysts and surface catalysts. And lastly, you also have light harvesting and vision process. And even for some of these problems, even DFT can't even solve even the simplest like single reference problems without even going into the multi-reference situations. So finding the getting chemical accuracy can be very difficult to reach when you have multi-reference problems, except for a very small number of molecules where the number of atoms involved in that molecule are relatively small. And from a chemical industry perspective, like quantum computing is thought to lead to like some killer application that can be used in the chemical industry's value chain. And we're going to focus mostly on the two first ones, which are the quantum simulations or using optimization or quantum AI or machine learning to solve these problems. And this can help us like design new molecules and solid materials that can help improve either for chemistry or pharma or in material science. And there's different families of algorithms that are used for these problems. Like, there's one family of algorithms is the quantum phase estimation, but this allows you to estimate the phase of the eigenvalue of some unitary operator. And the key behind this algorithm is the quantum Fourier transform. And we make the assumption that to use this algorithm is that you have some oracle that can prepare the state and perform the controlled U transformations. However, the problem with quantum phase estimation is that you would need a fault-tolerant quantum computer to be able to use it. So in the near term, what people use instead is the variational quantum eigensolver. So this is an algorithm that is grounded in the variational principle. And the aim is to find a parameterization of the wave function and compute the lowest possible eigenvalue of the Hamiltonian. And for this, you need an ansatz for the wave function that can be implemented on a quantum device as a series of gates. And lastly, another family of algorithms people have been looking into more recently are called the quantum embedding methods. So this is a divide and conquer approach. So you can break down the system into smaller pieces that are more manageable by simulation. And typically, this already was typically used in strongly correlated systems in condensed matter physics, and more recently has also found use cases in quantum chemistry. So this is a hybrid method. And one approach is to use a projection-based embedding method for combining variational quantum eigensolver with, for example, density functional theory. And this is called like VQE and DFT methods. But I'm mostly going to talk about VQE families of approaches, because otherwise this talk would be a bit too long for that. So for those of you that don't know what VQE is, this is also a hybrid approach between in which you do part of the computation on a quantum computer and the other part in a classical computer. So we start with a fermionic Hamiltonian, and then you find the Hartree-Fock wave function. Then you map this problem onto qubits, and then you generate an ansatz with some parameters theta that you can write in this form, and then you write it as a series of gates. And then you take a measurement to find your energy as a function of the parameter theta k, which is k is the kth step of your computation. Then you send this back to a classical computer that does the classical optimization, and then finds you the new values of your parameters that you send back to your quantum computer to restart the process until you find a converged energy. And of course, to do this, you have multiple choices of the ansatz, and there's different ways of doing it. You can find a hardware efficient ansatz. So this is an ansatz that is built specifically for given hardware to take advantage of its characteristic. But the problem is that this is not guaranteed to be a good approximation for the state of interest, because it doesn't take into account the chemistry of the problem. Another one could be the symmetry preserving ansatz, which takes into account the symmetries of the system that you are studying. But for chemistry, one more interesting one is the unitary coupled cluster ansatz. So for this one, involves like non-local gate operations and can be expensive to implement on current near-term devices that have a limited qubit connectivity. And lastly, people have also started looking at tensor networks. So these are like global wave functions constructed from the tensors that are associated with local degrees of freedom. And they can be a very good choice for low energy states and have shown to be very successful in classical simulations. And examples of these can be MPS, which is matrix product state, or PEPS, which is projective entangled pair states, or MIRA and DMIRA, which is multi-scale entangled renormalization ansatz, or the D in DMIRA stands for deep. So this is the deep multi-scale entangled renormalization group. And because the dimensions of the associated tensors grow exponentially with the depth of the quantum circuit associated with it, it is possible to prepare certain tensor networks with large bounds dimension on a quantum computer that presumably cannot be efficiently simulated classically. So this is why the tensor network approach have been quite interesting lately to look into as well. And the problem sometimes with VQE is that once you do your optimization, the solution that VQE gives you is not the correct one. And for example, if you have a system that you know that the correct solution or the correct solution should be the one that has, for example, 2 electrons, whereas the VQE gives you a solution that has only 1 electron. By knowing the type of systems that you have, you can then add some kind of penalty term in which you know that the local minimum will be for n equal 2, and this will just shift the solution and gives you a new cost function that has the optimal solution for your VQ problem. Yeah. How much? Oh, okay, 5 minutes. Okay, I'm gonna try to move a bit faster. Okay, so this is interesting, but however, the problem is that the cost functions may be too convoluted, making it more difficult to optimize, and you have an arbitrary choice of the weight parameters, which can affect the conversions of the functions. And lastly, I'm going to talk quickly about the different VQE-based excited states computation. So VQE originally was only for the ground state, but if you're interested in computing excited states, you have these different variants of VQE, and you have the papers associated with it if you want to look more into it. Because I don't have much time, I'm going to jump over the qubit mapping and move directly to the software that we have developed. So I'm going to talk quickly about CAMWI, QLAX, and QReports. So CAMWI is our in-house computational chemistry software as a service. So this would be equivalent to Gaussian for classical chemistry computations. And we have different features inside of this software for which you can compute the energies, the gradient, the Hessian, the dipole moments, transition amplitudes. And you can run this both on a simulator or a real hardware device. And one simulator that we use is QLAX, which is an open source library for simulating large, noisy, and parametric quantum circuits. And this is developed jointly between QunaSys, Osaka University, NTT, and Fujitsu. And you have here the link to the documentation and to the GitHub page of QLAX. And lastly, one of the last things we have been working on over the past year is called QParse. So this is also an open source library that offers some modularity and extensibility in the sense that you can use it either as is to run the algorithms that are already implemented, or you can use parts of it to build your own algorithms and develop this code base even further, and then contribute back to the open source code if you want. And it's completely independent of the platform and can be run both on simulators, of course, and real hardware devices. And we have shown, if you go to this page here, how this is actually performing compared to other open source libraries. And yeah, I think I should be almost out of time. So here you have like the different parts of this open source library that you can see. I've also shared like my slides directly, so if you want to go back to see, and I'll have access to the links. And lastly, we have also like tutorials in our website in which you can use to test the different components of this open source library, which can help you get started and also use different parts for your own coding next. So yeah, thank you for your attention.
Hi, thank you so much, Karim. It was great to see, learn about quantum chemistry. People have heard a lot about VQE. Not everybody knows exactly how it works. I think you covered a lot of very interesting ground, and
Thank
those
you.
last slides with the different tools. That's very interesting, and something I liked is showing how the different people or like organizations that are in the quantum space collaborate, for instance, to make QLEX, right? You
Yeah,
see universities and industry all collaborating together to make something that is useful for the field in general.
yeah,
For instance, you can find a plugin between PennyLane and QLEX, like you can use
yeah,
it, and a lot of people can use it for different uses, right? And also, you
exactly.
had a very nice logo for, I think it was for Curie.
Yes.
Very
Oh, for Kamui.
for
We,
Kamui.
yeah, we will have a logo for Curie, but that will be coming sometime later. Yeah,
Yeah, that's okay. Well,
yeah,
everybody, now you can
yeah.
go to the links that we shared in the chat. Make sure to
Mhm.
ask your questions. So you have last minute to ask your questions so that you can get to ask them live to Karim. If not, you can always ask them on Discord. But if you ask them in the chat, your name will be entered for a giveaway. Okay, so let's take a look at our first question. A question by Nub Cake. Is the ZX calculus useful for quantum chemistry?
Is what?
ZX calculus, is it useful for quantum chemistry?
That's a good question. What's ZX calculus?
ZX, like ZX.
Yeah, what is that? I don't know what
Oh,
CX.
it's a mathematical framework. Actually, we had a really cool talk on it.
Oh,
But
yeah. I don't know CX calculus, so I cannot answer that question, unfortunately.
well,
So hopefully, maybe someone can expand on it on the Discord.
we had a
Maybe
really
because,
yeah,
yeah.
exactly. If somebody wants to share links on the Discord or on the chat, we also had a good talk on spiders and a
Okay.
very like graphical way of seeing it. But it's also, of course, like mathematically has a mathematical
So I should
way
probably
of
watch that
writing
talk
it.
later on.
Okay, so I have a different question for you.
Yeah.
It's about how you got into quantum computing, right? We want to learn about you, like as a person, and how was your road into quantum?
It is quite interesting. So after my PhD, I moved to Japan for a postdoc in Okinawa, which actually I'm right now in Okinawa again. So it's one of the southern islands of Japan. And one student wasn't sure in which group to join for his PhD, and I convinced him to join our group in condensed matter physics. And that person is Andreas, who after finishing his PhD, he joined QunaSys, and then he asked me to join QunaSys to work with him on quantum computing. So I recruited him first into our group, and then he recruited me back into QunaSys. Yeah. So
Yeah.
yeah, that's how I
Uh,
got into quantum computing.
Getting to meet cool people, it's not only fun, but it actually helps you.
Yeah, exactly.
Okay, we have another question by D Nino 90. What is the largest molecule can solve the electronic properties for with quantum slash hybrid versus classical algorithms? So it's a little bit
Oh,
convoluted, but it's about what is the largest
yes.
molecule you can solve, like you can model.
Oh, that's a good question. Yeah, it depends. Like the problem is not just the size of the molecule; it also depends on its active space. So the largest molecule. That's a good question. I think. Let me just check the paper I was looking into. There's actually a paper I haven't had time to completely read. That I should maybe share in the Discord. Um, where is that one? So. Okay, I should look up that one. Yeah, I can look up the paper. So there's a recent paper about embedding methods by some people from IBM and Max Planck that actually just came out like this month, so a couple of weeks ago. And I think that one could have like more information about this, and I'll share it directly on the Discord, and that would answer the question. Yeah, just don't have
Awesome.
that information right now in my head.
So everybody, you know where to go. Make sure to keep asking your questions to Karim on the Discord. But don't go just yet. We will say goodbye to Karim, but everybody stay for a giveaway. So Karim, we're gonna have to say goodbye, but everybody else, make sure
Yeah.
to stay.
Okay. Thank you so much.